Hi, this is Martin from MB Drive Services. Welcome to our channel about variable frequency drives and drive systems. My topic today might be a little bit controversial because I would like to talk about differential protection of a VFD transformer. Protection in general is crucial for personal safety, for reliability, and to protect the assets of the user. And of course, transformer is no exception, and every transformer shall have a reliable, proven, solid protection concept that really works and protects the transformer. At the same time, differential protection is a very popular protection scheme for power and distribution transformers. It has specific characteristics that are superior compared to other protection methods. And the question here is whether to apply differential protection on a VFD transformer as well, and what might be also some challenges, maybe some restrictions. For that purpose, I have prepared a small sketch with a medium voltage drive system. We can see the input transformer in the dotted box. As you probably know, medium voltage drives often require a multi-winding transformer because they have a multi-pulse rectifier, especially if it's a diode rectifier, and the combination of the two shall eliminate certain harmonics from the spectrum so that the harmonics injected into the grid are low, are within the limits of the standards, and the need or the necessity for a harmonic filter can be eliminated. And then the question is whether the differential protection can and shall be applied on such a multi-winding transformer or not. Before going into the details and into the discussion, we make one step back. We look at the, let's say, simplest possible differential protection on a two-winding transformer. We have a current measurement on the primary side. There is also current measurement on the secondary side, and the relays comparing those two currents. Of course, the nominal current in amps on the primary and secondary side, they are different, but this is covered by the scaling of the CT or by referring to the percentage value of the nominal current. Now, I mentioned that the differential protection is appreciated due to some superior properties. Every protection scheme has certain objectives, and the three where the differential protection really excels are listed here. One of them is speed, so this is basically the reaction time, how fast, how quickly the protection scheme reacts. The faster the reaction, the safer for the personnel because of the accumulated energy from the fault, and the smaller also the damage on the hardware. Selectivity means this is defined, this is basically the protection zone where the protection function is active. So here for the differential protection, it's the delimitation of the protection zone is by the measurement points on the primary and secondary side. So differential protection is active in between those two measurements. And sensitivity is about the threshold where the protection function picks up. So in this case, the error in the current that causes the protection reaction. So on a simple transformer design, at least simple with regards to the number of windings, these are the superior characteristics where the differential protection excels. The question now is whether applying the differential protection on such a multi-winding transformer, whether we still have those properties, and whether there are also some limitations, restrictions, and possible also risks. So let's look at the implementation of the differential protection on a VFD transformer. I have again prepared a sketch. We can see three cases here. The first one is the simplest possible transformer, just a two-winding like we have seen. This simple transform can be used in VFD applications as well. It's not that common, but some active front-end type of VFDs would just require this simple, relatively simple two-winding transformer. So here the implementation is straightforward. We just measure current on the primary side, current on the secondary side, and we feed them into the differential protection relay that is then doing the job and comparing the currents. If we have a transformer like here, a three-winding transformer with two secondary windings, then the implementation is still quite simple. It's because most of the modern differential protection relays would support such a configuration, meaning you could select the winding connection or vector group of the specific transformer in the relay software itself. So it could be, for example, D0, Y11 or Y0, D1 as examples of a three-winding transformer. By the way, if you would like to learn more about these winding connections, vector group, and clock notation, then we have another video dedicated to this topic, and we have also a webinar that explains that subject in detail. But the point here is that we have two secondary windings with 30-degree phase displacement, but on a such still relatively simple configuration, the protection relay would support such configuration. So we can just feed the primary measurement inside and the two secondary measurements. The currents are phase displaced, they are not in phase, but the relay would consider that internally in the calculation. So it would sum those two secondary currents in a correct way, geometrically. It would consider the phase shift. However, if you have a more complex transformer, like this one, or even more secondary windings, then the relay would not support such configuration of the transformer inherently. So we need to find some workaround. What we can see is that as the number of secondary windings is increasing, we need more components besides the relay itself. We have, of course, the current measurement. So on the secondary side, if we have 6 secondary windings, we need 6 sets of CTs. So the number of the current transformers is increasing. This might also cause some considerations about the reliability. As the number of components goes up, of course the reliability goes down. And then as the windings are phase displaced, the currents flowing in each secondary winding, they are not in phase with each other, so we cannot just sum them up arithmetically. If you would just sum them up and feed the sum into the relay, then it would trip immediately. Because as I explained earlier, differential protection is appreciated mainly because of its sensitivity, and here we would have an error. The primary current would not be the same as this arithmetic sum of the secondary currents. So the relay would trip immediately, although there is no fault in the system. So this is of course not what we want. So we need to properly sum those current measurements. One of them we can take directly, and the other 5 we need to compensate for the phase shift. So that's why we have those phase shifting CTs, or compensating CTs that are compensating the phase shift. And only after that we can sum all of them and feed them into the relay. So we can see that the complexity, as the number of windings increases, we have more components involved, and we need to do some engineering around. here in those two cases, the relay supporting it, we can just connect measured signals and of course do the settings, but it's quite straightforward. And here we need to do some engineering around, which also increases some risk of wrong implementation, false stripping, so on. Besides the fact that we have a larger number of components, there are other aspects involved. One thing we shall also keep in mind is that the currents that we measure on the primary side is a clean current, so very close to a sine wave with low distortion. This is why we are using this multi-winding transformer and the corresponding complexity on the rectifier to minimize the harmonic distortion. So the current here has low distortion, is almost sinusoidal, is maybe 1, 2, 3% distortion. But the currents that we are measuring on the secondary side, they have pretty high distortion. I mean, each secondary winding is feeding one 6-pulse rectifier, so the currents have the typical harmonic pattern of that 6-pulse, so they will have very distinct 5th and 7th harmonic, 11, 13, and so on. So those currents are quite distorted. And then it's also a question how the relay reacts. Is it filtering the signals? Probably not so much, because the relay shall be sensitive and it shall be fast. And if we are filtering any signal, then we are introducing certain delay in the signal processing. And this is not necessarily what we want. It reduces the sensitivity and it reduces the speed. But it's something to consider how sensitive we can then set the relay, because this current is very clean and those currents are quite distorted. So of course a function or question if the CT is already, the measurement is providing some kind of filtering inherently, but it's also one aspect to consider. So generally, if you would ask me, back to the original question, differential protection on a VFD transformer, yes or no? I would say it's not black and white. It really depends on the topology of the VFD and the corresponding transformer design. If the transformer is simpler, like 2 or 3 winding, okay, no problem. It's very straightforward. The implementation is easy. The probability of some wrong implementation or wrong parametrization is relatively small. So there I would say it's for sure an option to consider. For a multi-winding transformer, so more than 3 windings, higher complexity, I would be definitely more careful. We see here that the number of components involved is increasing significantly, and also the whole protection scheme needs to be engineered, because it's not supported by the relay itself. We need to do some work around, some engineering around. This is also possible risk of wrong implementation. So either there could be some faults, which are not real, where the relay should not trigger, or on the other hand, the sensitivity would be much lower than expected. So one shall be careful. I mean, if you would say that the overcurrent protection is not sufficient for me, I would like to enhance the protection of the transformer, but I have a multi-winding transformer, then there might be some other methods how to add protection, how to add reliability and safety into the protection concept, and at the same time maybe not use this scheme, but some other way to protect the transformer. If you are more interested in the topic, you will find in the description a link to an article that describes this point about differential protection, and there is also a link to a webinar when we go really in detail and explain the implementation, the limitations, and so on. Thank you for watching.